Hello, I'm Samuel Shai, and I'm going to talk today about new directions in facet theory. In this lecture, I will review how facet theory helps us discover the structure of concepts, specifically the structure of multivariate attributes using smallest space analysis, SSA. Next, I will show how facet theory proposes to measure multivariate attributes using multiple scaling by partial order scalegram analysis, known as POSAC. Finally, I will present a new prediction model for behavioral sciences that emerged from my work in studying the relationship between concept space and measurement space, a model that amends the one employed by Gutmann and his contemporaries. So let's start with the structure of concepts, the component of the concept and the relationship between the components. Suppose you are an explorer who has a map of a new continent with several countries in it. In order to find out how the continent is divided into countries, you may choose a set of points on the map, and for every point you have chosen on the map, a local informer will tell you to which country it belongs. This is the game. With this information, you try to do the best you can to divide this continent into countries. In this example, we can have a fair idea about the location of the countries: the red country, the yellow, the black, etc. The analogy of the SSA map with the continent map highlights important principles of facet theory. Principles that make facet theory so useful for the analysis and interpretation of multivariate data. What are these principles? First, the attribute under study, for example, intelligence or attitude or health, is represented by a geometric space. Second, variables of the attribute are represented as points in that space. Conversely, every point in the geometric space is a variable of the attribute. This is the continuity principle. The variables we choose for SSA must be from the same continent, that is, to belong to the same content universe. This is ensured by including in the SSA only variables that have an ordered range with a common meaning. Hence, facet theory introduces a new scientific imagery. A geometric convex metric space represents the multivariate attribute, for example, intelligence. And here you can see some examples of a geometric convex metric space. By the way, convexity here is in the sense of metric convexity, not the usual Euclidean one. Each point in this space corresponds to an attribute variable. The observed variables, whose location was actually discovered, constitute but a sample from all points in the SSA map. The sixth principle: this sample of variables is used as marking points for inferring the partition of the SSA attribute map into distinct regions, each representing a component or a subdomain of the attribute. Finally, in facet theory, relationships between attribute components, such as verbal intelligence and numeric intelligence, are expressed in geometric terms, shapes, spatial orientation, etc., rather than in algebraic terms, such as distances or correlations. Just as we do when relating countries in terms of geographic orientation, not in terms of distance. These principles of facet theory have immediate consequences. The imagery of an attribute as a continuous space from which variables are sampled implies that clustering of variables in SSA map has no significance. It is just an artifact of the sampling of the variables. What matters is the identification of distinct regions with well-defined subdomains of the attribute. Facet theory uniquely proposes a way of transcending accidental clustering of variables by focusing on a robust and replicable aspect of the data. That is, the partitionability of the attribute space. Now, this feature of facet theory brings in new concepts, raises new questions, and opens new ways of understanding behavior. All these make facet theory a revolutionary scientific paradigm for behavioral research. Sampled variables that are clustered together may belong to different subdomains, just as two cities that are close together may be located in different countries. Conversely, variables that are far apart may belong to the same subdomains, just as two cities that are far apart may belong to the same country. Example, suppose the attribute we are investigating is the intelligence of a group of people. Following Louis Guttman, an intelligence test item is defined as a question that asks a testee to provide the most correct response to a cognitive task. Intelligence itself is defined simply as the set of all intelligence test items. And in general, facet theory advocates defining an attribute in terms of its observable variables. Now, in the case of intelligence study, the mapping sentence may look like this. Student P's response to a cognitive task that requires either recall or replication or inference of an objective rule in a verbal, numerical, or figural material is, the range is from very correct to very incorrect. The mapping sentence guides the stratified sampling of variables of a multivariate attribute. Using a mapping sentence, we can sample variables from the entire attribute content universe with its infinitely many variables. Now we want to see how inferences can be made from the sample of observed variables to the entire content universe of the attribute. In the case of the multivariate attribute of intelligence, it was found that the intelligence space can be partitioned into sectors, each containing variables pertaining to a single kind of material. In such a case, we say that the material facet is angular. Why? Because it varies with the angle. The cognitive task facet was found to partition the same space into concentric rings, each containing variables of a single cognitive task, either recall or replication or inference of a rule. In such a case, the cognitive task facet is said to be radial. Why? Because it varies with the radius. Superposition of the two facets yields the radix theory of intelligence due to Guttman, with its 9 regions, as you can see. Now, some of you may ask, why confine ourselves to just 3 kinds of intelligence materials? In principle, we would like to account for all possible kinds of materials, or at least to make sure that the materials included are drawn from a domain that is complete in some sense. For this purpose, the 3 kinds of materials, verbal, numeric, and figural, may be decomposed into elementary facets. The 2 elementary facets I propose are the environment, whether physical or social, and the symbolization level, whether it is low symbolization level, that is concrete, or whether it's high symbolization level. If we do that, we find that numeric material may be considered as symbolization of the figural or the physical world of objects, shapes, etc. And the verbal material may be considered a symbolization of something else. What would be the missing subdomain in this case? I propose that the missing subdomain is interpersonal material. And so we have a complete 2x2 scheme for providing a rationale for different kinds of materials in intelligence research. The 2x2 pattern of the new material facet, with the 4 elements in it, was empirically confirmed by faceted SSA. Now, in a study conducted at the Hebrew University Medical School, thirsty mice, very thirsty mice, were placed one at a time at the center of an 8-arm maze. At the end of each arm, there was a drop of water. For each entrance of a mouse, beginning with the 3rd down to the 8th entrance, 2 variables were recorded. 1, performance, whether the entrance was to a new arm with a drop in it. This is a correct response to the situation to reach a new drop of water. 2, directional consistency, whether the entrance was in the same direction as the previous entrance. That is, a rule was actually being followed. Lo and behold, a radix was found analogous to the human intelligence radix. You can see here that all the directional consistency, which we interpret as rule application, are inside a circle, while all the performance, which corresponds to memory, to sheer memory, are outside. And this is a very clean SSA that is very much analogous to what we found in the case of human intelligence, that the more complex function was inside and the less complex was outside. Now, faceted SSA of mice behavior, performance and directional consistency in consecutive days yields a partition of the behavior space into stripes ordered by the days. You can see day 1, day 2, day 3, etc. In such a case, we say that the day facet is axial. Why? Because it varies with an axis. Next, I would like to talk about generic theories. The radixes of intelligence behavior found in people and in mice point to facet theory's potential for discovering scientific generalizations or generic theories. Theories that are valid across a wide range of different research domains. A generic theory that has been found very fruitful is the faceted action system theory. You can see that this theory identifies 4 functioning modes for any action system. Functioning modes are the conservative, the integrative, the adaptive, and the expressive. These 4 forms of functioning are rationalized, again, by 2x2 scheme, namely 2 elementary facets that are binary. One application of the faceted action system theory is to the quality of life of human beings. The application of the faceted action system theory to the human quality of life equates systemic modes with subsystems of human functioning. Thus, the conservative mode is equated with cultural subsystem. The integrative mode is equated with social subsystem. The adaptive mode is equated with a physical subsystem, and the expressive mode is equated with the personality subsystem. All this is being explained in the appropriate literature, and you can find it there. The point of interest at this moment is that faceted action system theory predicts that the quality of life variables would be arranged in the same order as you see them in this table. And indeed, this has been verified in many, many studies. For example, in the study of Maya Benish, you have the picture here. You see that the cultural is opposite the personality, the physical is opposite the social subsystem, just as predicted by the theory. Now, the dual perspective of the data matrix means that rows represent the population sample, usually persons, and columns represent the attribute sample, the variables. In effect, we have here dual perspective for the same data matrix. The perspective of the columns, the perspective of the rows. Measurement is concerned with the rows. We now turn to structuring the population by focusing on the rows of the data matrix. Every row lists the scores of an observed person on the observed variables, questionnaire or test items. A profile of a person is the list of scores obtained by that person on a set of variables having a common meaning range. Our purpose is to create a theory-based measurement procedure for comparing and assessing population members with respect to the attribute under study. Two profiles are said to be comparable if each score in one profile is greater or equal to the corresponding score in the other profile. Otherwise, they are said to be incomparable. Examples you can see here. 1, 2, 1, 2, 2 is greater than 1, 2, 1, 2, 1. They are said to be comparable because one is greater than the other. However, 1, 2, 1, 2, 2 and 2, 1, 1, 2, 2 are incomparable. The first two variables, the one profile is greater than the other, but the other profile is greater than the first. And so I have another example. 4232 is greater than 3232, but 4232 is incomparable to 2432. And here we try to represent it in a two-dimensional space, preserving the order relations originally observed between profiles. And so we see that comparability relationship 4232 greater than 3232 is represented by the fact that the new profile, the new coordinates for the first profile are 6, 4, and for the second profile are 4, 3. Obviously 6, 4 is greater than 4, 3 because 6 is greater than 4 and 4 is greater than 3. I hope that's clear. Now, incomparable profiles such as 4232 and 2432 are represented by two new profiles, 6,4 for the first profile and 3,6 for the second profile. Just as these profiles were originally incomparable, so is their representation in this two-dimensional space, because 6,4 is incomparable to 3,6, because 6 is greater than 3, but 4 is less than 6. I hope that's clear. Multiple scaling by Pozak. How do we go on from here? Multiple scaling by Pozak transforms the observed profiles into shorter profiles that preserve order relations, incomparability as well as comparability. Pozak maps the shorter profiles into a coordinate space of suitably lower dimensionality. The example I showed you was two-dimensional. And Pozak suggests procedures for interpreting the coordinates as fundamental measurement scales. With the support of the United States Army Research Institute, we created a special computer program, Pozak LSA, for mapping many profiles in a space of small dimensionality so that order relations, incomparability as well as comparability, are preserved. For every variable processed by Pozak, the program optimally partitions the Pozak space into two regions of low and of high values in that variable. Here's an example, quality of life measurement. A simplified mapping sentence says the well-being of respondent X in the mental, physical, social, cultural life domain is found to be high, score of 2, or low, score of 1. A two-dimensional Pozak was found to represent order relations between the observed profiles, assigning just 2 scores, x, y, to every individual instead of the original 4 scores. For every person, we now have just 2 scores given by the 2 coordinate scales, x and y, replacing the 4 scores observed. This parsimonious measurement will be complete only if we discover the meanings of the 2 coordinate scales. The coordinate scales are interpreted by studying the behavior of the variables in the Pozak space, where in that space is each variable low and where it is high. Cultural well-being, a vertical line partitions the Pozak space into regions of low and high values in this variable, thus associating it with the Pozak x coordinate. This was found empirically. So we say that cultural well-being, in this case, is an x-polar role, plays an x-polar role. An orthogonal line partitions the Pozak space into regions of low and of high values in the variable physical well-being, associating it with the y scale. We say that the physical well-being is a y-polar role. For the next item, social well-being, no simple line was found to satisfactorily divide the space into high and low values, but an L-shaped line was discovered that does the job. It associates the variable social well-being with a minimal level in x and a minimal level in y. If you are high on the social well-being, you are not very low, neither on the cultural well-being nor on the physical well-being. An inverted L-shaped partition line was found to satisfactorily partition the space between low and high values in the mental well-being. Inverted L-shaped partition line associates the variable mental well-being with the highest level in the x-coordinate or the highest level in the y-coordinate, or both. Superposition of the 4 partition lines creates a two-dimensional measurement space that you see in front of you. It defines 4 intervals on the x-coordinate scale and 4 intervals on the y-coordinate scales. And we now need a new name for each variable, for each scale. So we interpret the x scale as the graduated cultural quality of life scale, because it's based on the cultural well-being, partitioned further by the social and the mental well-being. And the same for the vertical axis, that is the y-coordinate scale. We call it the graduated physical quality of life scale. It's based mainly on the physical well-being, but it's finely graduated by the social and the mental well-being. And of course, when we have many finer mapping centers, as we do, with 16 variables, then the quality of life measurement space is much more fine. It has 7 or 8 different intervals that are meaningful. Let's go to the next example. Evening TV watching recorded by whole hours. Did person P watch TV last night in the hour 7 to 8, 8 to 9, 9 to 10, 10 to 11? Yes? 1? No equals 0. A person with a profile 1001 watched at 7 and at 10, but did not watch TV at 8 or at 9. A person with a profile 0011 did not watch at 7 and 8, but did watch at 9 and 10. Here is the one-run hypothesis. In the evening, people usually turn on their TV once, watch for some time, then turn it off. In a large representative sample of population P, only these 10 profiles out of the 16 possible ones actually occurred. We can see here in the list of profiles, the only profiles that do occur are those where the hours watched are close together, form one sequence. The 10 profiles fit within a two-dimensional space while preserving all ordered relations between them. This can be done by hand, but usually a computer does more complex empirical data. Now, we want to interpret the coordinates, x and y. How do we do that? Well, while inspecting the x scores, 1, 2, 3, 4, we conclude that the x score represents the latest hour in which TV was watched. Score of x equal 1 goes to those whose latest hour is the first hour, 7 o'clock. Score of 2 goes to those whose latest hour of watching was the second hour, 8 in our example, and so with the third and the fourth. The y-axis also measures this time how early was the earliest hour. The earlier is the earliest hour, the higher the score on the y-axis. If your earliest hour was very early, like 7 o'clock, then you get a score of 4. If the earliest hour you watched was only the second hour, 8 o'clock, then you get a score of 3, and so down to 1. If your earliest hour was the last hour, what was 10 o'clock, then you get a score of 1, a low score. The interesting thing about it is that both these axes, the x and the y, tell you in a way how much TV you watched when every other conditions are equal. The greater is x, the more you watch TV. The greater is y, the more you watch TV. And this is very beautiful because it preserves, it means that this space preserves the common meaning range of the original variables, watch or not watch, in each hour. This is a nice feature of the POSAC, that the axes preserve the common meaning of the range of the original observed variables. Example 3 is Guttman scale. Some of you may have heard of Guttman scale. If all observed profiles are comparable, then a single scale suffices to represent all order relations between them. Any set of ordered numbers may serve as a scale. For example, the natural numbers. In this example that you see in front of you, we have 6 profiles and each is assigned a new score of just 1 digit, as you see, and that's enough. But any other ordered scale may be used. For example, we can use the sum of the original scores. In fact, this is the only case where summation of scores is indeed justified. Guttman scale is a hypothesis that observed profiles are all comparable. Example of a Guttman scale is here. We have a mapping sentence. Suppose person X believes the child and not his parents should decide which high school the child should go to, which university the child should go to, what subject the child should major in at the university, and what occupation the child should follow. And finally, whom should the child marry? If you believe that the child should decide any of this, you get a score of 1. If you believe that the parents should decide it, you get a score of 0 on that item. Here is an hypothesis. The 5 score profiles obtained in a survey of parents will form a Gutmann scale. Now we have to check it, whether it's true or not. The rationale for this hypothesis: anyone who says yes, the child should decide on any one variable will be likely to say so on all variables that follow. For example, if you believe that the child should decide which high school to go to, you most probably would also say that he should decide which university he should go to. The next example is the measurement of creativity from a study I did with Eritios in 2004. In this study, we identified by SSA 6 creativity types based on the material facets: interpersonal, figural, verbal, numerical. These are the same as the intelligence materials. And 2 additional types of materials: presented figure ground creativity and imported figure ground creativity. I will not go to the exact definition, but roughly, presented figure grounded creativity means that the creative solution is reached by looking at the presented objects or presented elements. And imported figure ground creativity means that the solution must be reached by importing elements from far away, from a different context. The partition lines found in the empirical data in the POSAC space, it was found that the 2 polar variables were figural creativity, which in this case was a y-polar, and interpersonal creativity, which formed a x-polar variable. Success in the attenuator, numeric creativity, ensures minimal level in both the x interpersonal creativity scale and the y figural creativity scale. Success in the accentuator, imported figure ground creativity, indicates especially high levels either in the interpersonal creativity scale or in the figural creativity scale. Bends in the partition lines induce graduations on the x and y scales. 3 bend partition lines induce additional graduations. In the case of verbal creativity, we have 3 bends, and also in the case of presented figure ground creativity. When all partition lines are superposed, we get a full measurement space whose scales are x, the graduated interpersonal creativity, and y, the graduated figural creativity. This is the multiple scaling by POSAC, appraises every person's creative ability by 2 fundamental scales: the graduated interpersonal and the graduated figural scale. Finally, I would like to show you how the procedures of facet theory that I have described, namely SSA for structuring the concept space and POSAC for constructing the measurement space, how they have led to revising the classical prediction paradigm. The classical prediction paradigm that guided Louis Gutmann's scientific work and was accepted by scholars of his time is given by the matrix formula. D, the data matrix, equals U times V, where U associates the n observations, say people, with m factors, and V associates the m factors with small n variables. The idea is that if you find the underlying factors and their link to the variables, on the one hand, and the link between people and the factors, you can predict or reproduce the observed data matrix D. An important feature of this paradigm is that the same small number of factors characterize both the variables and the population members. But difficulties in applying this paradigm led Gutmann to believe that the matrix formula is to be understood not literally but metaphorically as a general scheme to guide research for lawfulness and prediction in behavioral science. He consequently softened the notion of measurement in his seminal paper, Measurement as Structural Theory, 1971. But as I found, behavioral prediction paradigm requires factor differentiation. Insights gained from mathematically associating faceted SSA and Pozak led me to amend the classical prediction paradigm. The new paradigm, published under the title of Modern Facet Theory, 1998, differentiates between factors of the attribute variables and factors of the population members. Two different kinds of factors. Modern Facet Theory prediction paradigm says that D is U times M times V, where D as before is the data matrix, U associates the N observations, the people, with the P Pozak coordinate scales, which we can call the persons factors, if you like. Let's jump to V. V associates the Q facets with the N variables. And M, this is the new element in this model, associates the Pozak coordinate scales with the SSA facets. It associates the two kinds of factors. The discovery of M in substantive research domains is the challenge of modern facet theory. In every research you do, if you run both SSA on one hand and Pozak on the other, you have the substantive challenge of associating the facets with the coordinate scales. Associate in the substantive sense, in the contents. Now, here is a graphical scheme of the evolution of the prediction paradigm. We start with the classical one, D equals U times V. And then this branches into Gutman's scale, where from a single score, you can predict the entire profile, the observations, if indeed Gutman's scale exists, is verified. And the other branch says Gutman's simplex. This is the arrangement of variables in space in one dimension. Now the Gutman scale evolved to Pozak, partial order scalegram analysis, with an interpretation of the coordinate scales. Gutman simplex, on the other hand, progressed to the faceted SSA, interpreted coordinate partitions. Both together yield the integrated facet theory linking Pozak and SSA through M, that matrix that links the two kinds of factors, and to yield D equals U times M times V. Now I'd like to summarize by highlighting some of the main points that I made in this lecture. First, the continuity principle, defining a uniform texture on the attribute space and on the measurement space, which provides the basis for regional analysis. There's no regional analysis unless you assume continuity. Second, we have shown Cartesian decomposition and completion as rationale for choosing facet elements. Third, we mentioned the possibilities of generic theories. Facet theory can facilitate generic theories such as intelligence, as I showed in different contexts of mice and men, and facet action system theory. Finally, I have shown a new prediction paradigm which defines modern facet theory and its challenge, finding in specific applications the substantive theoretical link between facets of the SSA attributes and the coordinate scales of the Pozak measurement space. Thank you.